Alright guys, so we are going to try doing a graphical solution for the speeds or velocities around a linkage. In this instance, I will have a linkage that has a fixed length of 70 millimeters, a crank that is 20 millimeters in length, and we'll do our velocity solution when theta 2, the angle between the crank and horizontal, is 50 degrees. A coupler that is 60 millimeters long, and a rocker that is 50 millimeters long. We're also told that omega 2, the angular velocity of the crank, is 1 radian per second. So, the first thing that we must do if we're going to have a graphical solution of a problem like this is to have an accurate dimensional drawing. I'm doing this on 10 millimeter by 10 millimeter graph paper, so it's going to be fairly easy to do. I'll first mark out my fixed link, 1, 2, 3, 4, 5, 6, 7. So here is one end of my fixed link. We will mark that as 03, and we'll put 01 at the origin. Next, I will need to draw my 20 millimeter long crank. And this is at 50 millimeters. There are obviously multiple ways to do this. We could use trigonometry in order to figure out the run and the rise of a 20 millimeter length at 50 degrees. In my instance, I am going to use a protractor. My protractor is part of my little kind of nifty drafting card. I've had this for a number of years. It's really handy. It has both imperial and metric sides. So it's kind of a neat little tool. In order to do this, it's a little difficult to line up, but we'll get it there at some point. There, that should do it. And I want this to be at 50 degrees. So 10, 20, 30, 40, 50. And I'll just make a little mark here. And now I need to draw a 20 millimeter length line from the origin in the direction of the point that I just created. So there we go. It's not quite perfect, but it's good enough. So this, I can label right now, is my crank, and we'll usually identify that with a lowercase a. My coupler and my rocker are 60 millimeters and 50 millimeters. Again, I can do this one of several ways, but the way that I found that is easiest is to use a compass or something similar. My little drafting card does have a compass function. I just need to be able to use a separate drawing tool to hold one hole while I strike an arc with the other. So first I'm going to draw an arc for my coupler at 60 millimeters. I just put the whole of my card on the end here, and now I can draw an arc. I will have to shift the camera just a little bit in order to have space. 10, 20, 30, 40, 50, 60. So I will take this all the way out, get some lead back out in my pencil, 10, 20, 30, 40, 50, 60, and I'm going to draw an arc. There we go. Now the next one that I need to do is 50 millimeters. And this is going to be from my O3 point. So again, I will hold down this point. 10, 20, 30, 40, 50. And there we have it. A little messy, but not too bad. This will allow me then to draw a quite reasonably accurate figure. Not perfect, but reasonably accurate. And there we have it, a 4-bar linkage. We identify this point as point A, and the point up here as point B. Now, this technique is dependent upon treating each of these links as a vector. So technically what we're doing is saying that vector A plus vector B plus vector C plus vector D is equal to 0, the definition of a closed kinematic chain. In order then to create what we're calling a velocity polygon to figure out the velocities around this link, we're just taking the derivative of each of these vectors. So it'll be A dot plus B dot plus C dot plus D dot. These must also equal 0. We're able to simplify this because our D, the fixed link, does not move. So D dot becomes 0. Therefore, we only need to draw 3 vectors in order to describe the velocities around here. We are given omega sub 2 as 1 radian per second. And from the equation, V is equal to omega r, we know that we can calculate the velocity at point A. This implies that the velocity at point A is equal to 1 radian per second multiplied by the length of the vector A, 20 millimeters, or 20 millimeters per second. Started to run out of paper there, I apologize. So here's how we perform the velocity analysis graphically. Since I'm starting at point A, I'm going to treat point A as a fixed point for my velocity polygon. We've also learned that the velocity vector for any point on a link is perpendicular to the straight line between the reference point and the point in question. So the velocity of point A is perpendicular to the direction of this O1A vector, or link A. Furthermore, we can say that since this is 1 radian per second and it's given to us as a positive, that means that the rotation direction is counterclockwise. This can be found just by looking at our x and y axis and using our right hand rule to see that the vector is coming out of the paper. That's the positive direction for z, and therefore my fingers are telling us that the positive rotation direction is counterclockwise. So what that tells me to do is to draw my vector perpendicular to A, and I'm going to draw it at a length of 20 millimeters to represent 20 millimeters per second. Now, I can use two straight edges in order to create this line. There we go. Draw it in there. So, this perpendicular line represents the velocity vector of point A and its direction at the instant that we're looking at with this link in this position. I'm going to go ahead and label the points of my velocity vector. The starting point I will call lowercase o, just to treat it as a ground, and the ending point I'm going to call lowercase a. I know that's a little confusing because we're also labeling this vector as a. Maybe we'll call it lowercase v sub a. There we go. Now, I can see, I don't know what the magnitude is, but I know that the velocity vector of point B with respect to point A is perpendicular to the straight line between them. And from the standpoint of drawing a velocity polygon, that vector is going to intersect the vector for the velocity of point A right at its end. So I'm going to go ahead and strike just a line perpendicular to my coupler. And for this, little triangles are really handy. I don't know what direction it's going. It could be going either way, but I do know that it's going to go like this directionally. It's perpendicular here. The last one that I will need to draw in order to figure all of this out will be a line that's perpendicular to O3b, or our D vector, C. This will represent the velocity of point B with respect to our fixed reference frame. So since it's with respect to our fixed reference frame, it's also going to pass through this O point. So let's go ahead and create a vector that is perpendicular here, running through that point. And it needs to intersect the line that we created for the velocity vector that represents the velocity of B with respect to A. So what this does is firm up my lines. I will call this point down here V sub B. This triangle then is my velocity vector. I can erase the part of the line that I drew due to the uncertainty And these links, the lengths of each of these lines, represent the velocities of the points around this mechanism. So as you recall, we made this line from lowercase o to VA equal to 20 millimeters to represent 20 millimeters per second. Now I can measure this line from VA to VB. This represents the velocity of point B with respect to point A as my mechanism moves. So let's go ahead and measure that. And I get, let's see, about 16.7 or 16.8 millimeters. So that tells me that my velocity of B with respect to A is 16.8 millimeters per second. I can now measure this line. This gives me the velocity of B with respect to the ground. And I get about 6 millimeters per second. Taking advantage of this equation, V equals omega r, that will allow me then to calculate omega sub 3 from the velocity of B with respect to A. It's going to be equal to 16.8 millimeters per second divided by the length of this link B, 60 millimeters. .8 divided by 60 is 0.28 radians per second. Similarly, I can determine the angular velocity omega sub 4. It's the angular velocity of link C. It's equal to 6 millimeters per second divided by the length of link C, 50 millimeters. So let's get that. Or 0.12 radians per second. Now, I can tell you that with practice, this method will get you within about 5 to 10% of a calculation method. The larger your figure is, the better off you are. It's a little easier to measure things that are larger rather than smaller. And the more accurate your sketch is, the more accurate your results will be. I have done this problem separately, actually in a CAD program. And what I got in CAD, go ahead and write this down, was that the velocity of B with respect to A was equal to 16.7 millimeters per second. And the CAD program gave me the velocity of B at 5.9 millimeters per second. If you do this in a CAD program, your results are just as accurate as if you were calculating it with one of the more involved algebraic techniques. In conclusion, I'm going to be assigning this problem to be done as homework, but we won't get that assignment until the next lecture. And what I would like you to do is try and duplicate this analysis using one of the calculation techniques. This concludes this video. I hope that you found it interesting. I'm sure that it was wildly entertaining, and I'll look forward to seeing you in our next class.